Okay. I guess we're good to go. So. Hey, let's start, everyone.
Okay, that's my deal.
Better mic volume. Can you guys hear me? Let's stop yelling. Voice at start. Look, on purpose I came earlier. I'm only 3 minutes late, so that's not bad, right? So today, actually, again, I hope I'm recording and everyone on Zoom can hear me and can see my screen as well, right? So today we start actually one of the most exciting topics in this class. Actually, I'm excited about almost every part of it, but this is cute because this one is really explains you how machine thinks about your programs, right? So remember, I was trying to explain you before that we do this fetch, decode, execute loop, and I was trying to give hints about how this internal organization of the CPU thinks about your program, right? But today is actually the first concrete introduction to how it's happening, right? So it's kind of exciting. So, and what specifically we're going to be doing? We're going to be looking at the Mips instruction set. So it's quite a, I mean, for quite a while, Mips was kind of dormant, right? So no one was really thinking about Mips much. And everyone was excited about x86 because x86 conquered the world and all the PC machines were running x86. But then kind of ARM came right on the mobile devices. I don't know how x86 actually missed that opportunity, but they did. And so ARM conquered the mobile world, right? But ARM is still a closed ecosystem, right? And so people who the parallel here is similar to Linux, right? So at some point, Linux became the de facto operating system in a data center. And partially the reason for that is that it was completely open. So people who were willing to do something with it could just take it and modify it in any in any possible way. And so now Mips came as an instruction set for RISC-V, a new open CPU architecture. So essentially, knowing the Mips architecture gives you some practical advantage, right? That's observation number one. Observation number two, that it's not too far off from other instruction set architectures. So ARM and x86 are conceptually similar, and maybe I will spend a little bit of time and touch on x86 instruction set. The book touches on ARM, right? So they are, I mean, the reason for that is that all these machines are built on the same principles. Essentially, initially people architects were exploring multiple organizations, but in the end they converged to the same thing, more or less, right? And that's why those architecture sets are similar. Okay. Remember my introduction speech where I was saying that you typically start with a high-level language, something like C or Java, right? You invoke compiler, and compiler translate this high-level program into low-level representation, right? And this low-level representation can be executed by the machine. So it's called it's a collection of machine instructions, which your CPU actually understands, right? So. And the collection of this machine instructions is called this, let me just change the thickness here, instruction set architecture. So essentially, there will be a collection of commands which a specific CPU understands. And if you keep your program in memory as a collection of those commands, and you point the CPU to the beginning of the program, it starts executing it, and it will gradually execute one instruction after another, right? And if you want to see some result, it will either put it in register, or as I was trying to explain, you can actually output something on the screen as well, right? So not that hard. And those instruction sets, the collection of those commands, they follow certain principles, and they're kind of intuitive. So there is not that much to discuss, but the main principle which won in the end is that the instruction set, which allows you to keep the hardware simple, allows you to perform deeper optimizations at the level of silicons, essentially in hardware, right? And so that's why essentially CISC or complex instruction set lost to RISC, reduced instruction set, right? And MIPS is this reduced instruction set. This is what we're covering here. As you will see, MIPS is relatively simple. It's so simple, it's probably one of the simplest instruction sets that I ever seen. And that's another advantage for this class because it's very easy to understand. So it's just one chapter of a book, right? Question?
Is x86 and ARM also RISC?
No, as I was mentioning probably last time, ARM is RISC, but x86 is CISC. And remember, I was telling that internally, they had to come up, they hit the wall at some point because they were not able to optimize, I mean Intel, they were not able to optimize these complex instructions, and they now translate complex instruction set into a reduced instruction set internally. This translation is a very first step, which their pipeline does. And they keep this translation in a cache because translation is reasonably expensive. And so they cache the results and they execute, essentially internally, they try to execute simple instructions over and over. That's again, it's kind of unusual how it plays against you, but they can't drop it because for backward compatibility reasons, right? It kind of bites them over and over. And a second, which is again, it's kind of like, the book likes to call those principles, but there's kind of like, I would call them sane design choices, right? What they say is we want to keep instructions regular, meaning that you will see that there will be, roughly speaking, 3 or 4 groups of instructions and 3 or 4 groups of encodings. And they internally, everything what you can fit within the group is almost identical. There's just different number which distinguish one instruction from another. And so this allows you to simplify the hardware. So you will see that they try to keep, to kind of like put them in groups and like implement them like that. Okay, so here's the first example. So imagine you have a line of C code. And I understand that not everyone knows C, but I can say a line of C++ or any other language, right? So it's almost identical. So we take B and C variables and add them and put the sum back in A, right? So in this, in a human readable assembly code, this MIPS, which I have here, we can write something like add, which says, okay, this is an operation, so this is normal. Take B and C as operands and put the result back in A, right? Let's for a second forget, you can't really write this line in the MIPS assembly just because variables are really regions of memory. And we'll talk a little bit about it, right? But intuitively, at least it gives you a hint, right? So all these instructions in this MIPS instruction set, they look somewhat similar, right? And this encoding or representation seems natural. Like if I would ask you to come up with this instruction set, and maybe I will assign it as a homework, or I will assign to like modify instruction set, you would come up with something like this. Agree? Okay, so it's important to, again, like a little bit of a terminology here. So this is called assembly code. This is just still some line in some language, right? So if this was the C language, the high level language, which you all probably used, this is still a line in a language, right? It's called an assembly language, right? And so you still need a translation, right? You still need some kind of a tool which will translate this high level human readable representation into a collection of bits, right? And this collection of bits can actually be executed by the machine, right? So this is called a machine code, right? They agree with this? So just to understand that there is kind of like 3 layers. And sometimes assemblers do more sophisticated conversions, kind of like, what can you do? Sometimes you run out of registers, or it might load. That's what the book at least says. And so you might like insert a couple of those machine instructions, but really it's rare. So typically assembly is kind of one-to-one conversion to machine code. Maybe you will like, what assemblers typically do if you insert like human readable labels, kind of like full or beginnings of the loop and stuff like that. So assembly will keep track of addresses of those labels and automatically insert them into your machine code, because those, as we will see soon, those some subsets of those bits will be actual addresses here, right? Agree with that? So all good for now. Okay, let's take a look at this example. How can we translate this? So it computes a sum of 4 numbers, B, C, D, and E, puts result into A. So how will we do this? Kind of straightforward, right? So almost embarrassing to ask, but let me still ask. So everyone thought about it? Okay, go ahead.
B and C, that means they're intermediate values, and then add the E, and then have the intermediate values in the
Yeah, you can what you're suggesting is kind of like write this. So add, like, let's introduce like T0 temporary value, B, C, right? Add T1, D, and E, right? And that maybe you add T1 and T2 and put the result back into A, right? So what is it? T0 and T1, right? Agree? Okay.
I was gonna say, could you do add B, B, C, update B,
Yeah.
B plus C?
Yeah, you can. Like what you're suggesting is instead of doing, maybe I actually have it here on my next slide. Yeah, it's different coding. But what you're saying is that what you can do instead, you can say, let's keep one temporary variable and just essentially say something like first B and C, and then keep updating it, accumulating the sum. Or you can even like, why bother about temporary variable? So you can say, let's put A here, right? Why not? Because that's the final sum. And then you can say, okay, I will be updating A again, but I will add now D to this. And then my last instruction will be again A, and updating A, it will be E, right? So those two encodings are surprisingly similar, right? They both take us 3 instructions. One of them, however, requires 2 additional registers, temporary T0 and T1, right? Or maybe, I mean, I said registers, so kind of like jumping ahead of myself, but you can see that maybe if you're running out of registers, then the first encoding is better, right? Question.
How could you just do add A, B, or A, comma, B, comma, C, comma, D?
Why can't you do this, right? Okay, that's a great thing. So the question is the following. Why can't you just do add A, B, C, D, and E, right? So who can tell me why can't you do this?
This operation only takes 3 inputs. You only have
Right.
one store it, and then the 2 values that you're adding together.
Exactly. So our machine only understands this simple instruction, which takes 2 arguments and puts the result in a 3rd one. And that's a great question. Like it's kind of a partially philosophical, partially practical question. Can't you build this? Can't you build a machine which, okay, like why not to build a machine which understands this operation? So your argument is a software engineering argument. So you say that then it will be hard to program, right?
Yes, and one thing that the established is that our company
Correct. So then your other comment, you say essentially that at some point you have to stop, right? And you say, look, why don't I add like something more here? But then you say, look, if I want to support all of it in hardware, it complicates my chip design. And typically this is this design principle, which was here, which says both of them actually, keeping the hardware simple and also keeping instructions regular. So regular means that it's easier to design the hardware because it will be supporting the whole class of instructions because it's all almost the same. And second, it also simplifies the program to a degree. However, that said, you might come up with some, you might be doing some very, very funky computation. Imagine some kind of a dynamic molecular simulation for just the sake of it. And imagine you recomputing some kind of forces, which you have to compute in every step. And maybe this force really
takes whatever, maybe it takes not 3 arguments, not 2 arguments, but maybe 4 or 5. And you are so desperate to compute this dynamic molecular simulation fast that you say, look, I will design custom hardware. Maybe it will be not called add, but it will be called something like add 5. And you say, on purpose, I understand that this instruction is so frequent in my workload, in my program, that I want to optimize for it. So it's not uncommon. And good example, so give me an example from real life. So when it was done recently, or like recently, like in modern CPUs, in modern chips, those kind of optimizations, which seems, okay, go ahead.
Like video encoding, is that one?
Video encoding, possible, actually, you're probably right. And unfortunately, I'm familiar with video encoding, but most likely they optimize for some common case. I remember someone last time who was there, and I don't know if that person is in class, was mentioning the tensor operations, which are like whatever. So, right, so it happens, right? So instruction sets do evolve. And I can give you another example. So now most chips come with crypto accelerators, because you say, okay, I want to encrypt all the traffic, in like network traffic which leaves this machine for whatever purposes, right? For security purposes and privacy. And those crypto operations they kind of have a specific shape, right? A specific algorithm have a specific shape, and that you can come up with a subset which has to be optimized. And so those operations are optimized in hardware. And unfortunately, I'm going further away from the main topic, but let me just finish here. You will see more and more of it. Remember, I was saying that we're kind of hitting this limits of architecture, and they cannot optimize generic single core chips anymore. And you will see more and more accelerators, which will bring more and more extensions to instruction sets. So keep an eye on it. But anyway, so back to this encoding, right? So you can either, this is what you were suggesting, updating A, or just using some of this as temporary variables, and I introduced my own registers here, but you can do this way as well, right? But at least we kind of understand how it works, right? Any questions about this first 2 examples? Right, so just additions for now. Oh, good. You.
Is the time on accessing those different variables that you create one compared to accessing A or is that the same?
Yeah, that's a good question. Let me get to this in a second. So, because in general, accessing variables in memory takes you a lot of time, as I keep saying every class, right? In every class. So really, in practice, this is not how this machine operates. So really, it will be operating only on registers. But just let me get to this in a second, and then we will be optimizing. Like, yeah. So you will. A short answer: if you can fit everything in registers, you will be okay, right? Because you can access the register in the same cycle, so you're not losing anything. But every access to memory may take you between. Remember, I told you multiple times, if it's well predicted, it might take you 2 to 3 cycles in the cache. If you're unlucky, this number progressively grows up to like 100, something like 200, 250 cycles when you really go to memory. Okay. No subtraction example. So kind of, again, not many surprises here, but I will introduce yet another operation here, which is sub, which operates in a similar manner. So it just takes, subtracts one from another and puts result back here, right? So what the encoding here is that we take this G plus H in a temporary register T0, then take I plus J, and again, put them in a temporary, put addition in the temporary register T1, and then subtracting T0, T1 from T1, subtracting what? T1 from T0, right? And putting back the sum, the subtraction result in F, right? In the variable F, right? Okay, so I kind of started like saying, okay, look, I'm like using those registers and stuff like that. So we'll come to it in a second. So right now, just believe that it's close enough to be practical that this is how it is. Actually, I came to this faster than I expected. Okay, so let's talk a little bit about what does it mean to access a variable, right? So in a language like C, right, we used to those things like variables. So we say int I don't like this, into A, right? And you declare a variable. What do you think is actually happening at this point? Like, what does it really, I understand, like you type this, then you went through a compiler, which, let's say a compiler, which generate, I mean, you can say that we generate assembly code, but let's say we actually generate machine code. What happens to these variables? Do you guys know? How is it represented in memory or in register? So where is it even? Right. So what you're saying is the following. So the compiler, and let me actually make you a drawing real quick, because I have only limited drawing capabilities in this PowerPoint or whatever, Libre, OpenOffice, but here I can draw freely. Let's talk a little bit about how programs are presented in memory, right? And I talked a little bit about it, but roughly speaking, the representation is the following. So you have the code of the program. And imagine this is all memory. Let's even like imagine that this is address 0 and your memory goes to some address max here on the right, right? So when you do something like A equals B plus C, so those machine instructions which we were talking about, they will be somewhere here in memory, encoded as collection of zeros and ones, right? I agree with that. And the alternative name for this part of the program is also called text. Roughly speaking, because you can read the program as text, right? However, we say, okay, what happens to this variable? For example, int A, right? As you mentioned, the compiler says, okay, I'll keep track of how many variables I have. And it gets a little bit tricky with global and local variables, but imagine that this is a global variable declared in a global scope. You can also call them static, because in C, you can write something like a static keyword, right? So what compiler is doing in memory, it will reserve some region, right? And say that this is where the A will be sitting. And imagine each box has 4 bytes, right? So A will be sitting here. If I have more variables like B and C, there will be sitting somewhere here. And this is some address. Let's call it A, for example. And the compiler actually computes, because upfront, you don't really know what the size of the code section and the size of the data section. And this section is actually called data. Right? Agree or believe? Any questions about it? So let me jump ahead a little, right? You probably have heard the notion stack, right? And a notion of heap. It gets a little bit, so roughly speaking, and again, I'm not going to explain right away what stack is and what heap is, and I'll come back to it. But those also will be locations in memory. So the stack will be here, or like if you like, let's call this part of the heap. It's more realistic, and the stack that's allocated here, right? And there might be some gaps. They don't have to be continuous in memory. It's just that you need to keep track of where they are, and compiler does it for you. And the assembly does it for you if your final step of compilation is actually like assembly language versus compiler just go directly to the machine code, right? So now we got this idea, right? So imagine this variable A is sitting here in memory, right? So really before, we can either say that my instruction addition, which was, we wrote like A equals B and C, either we should agree that those things, those names which I put here are either addresses. And then we essentially, the hardware will go, and when it will try to execute this instruction addition, let's imagine it sits right here, encoded in some machine representation, add A, B, and C. So when the hardware will be executing this instruction, it's either will go to this location A, B, and C, and that's possible. Or you say that those variables should first be brought to registers. remember I mentioned that registers are kind of close to the CPU. You can think of them as very small memory, only 32 registers, right? But you say that if all my instructions will be operating on registers, kind of saying addition will really be, I don't know, register 2, result, register R1 and R2, right? What you need first is you need an instruction, kind of like a load, which will bring something into those registers. And you can say that this brings an address of B, right? Does this make sense? So you say, now I get a little bit more concrete. So let me just, let me save this so we have it for future. I can say it like this for now. So in case it would crash. Right. So this is essentially what this slide is explaining here. So it says that as you were mentioning in your question, you said, okay, is it cheap to go to memory? So the answer is no. That's why we bring the value from memory into register once, and then keep accessing the values in memory. And when you run out of registers, you may be saving something back in memory, right? And that's why we call those registers scratchpad registers, right? But just think of them as registers are simply a very, very fast memory, so fast that you can access it within the same cycle. So you don't even lose a cycle, right? And in this instruction set, all instructions like addition, subtraction, everything will operate on registers. And there will be a subset of instructions which are memory load and store instructions, which simply bring values from memory to registers, right? So that's how this instruction set will be organized, right? And that allows you to do any sort of tricks, right? If you have a large number of variables in C program, right? The compiler generates the code, which gradually brings some of them into registers. You compute something. If you have enough register space, it stays there. If you don't, you just save it back into memory, right? And every time you read something from memory or write something back from memory, you pay a little bit of a penalty, right? In a good case, it's just 2 to 3 cycles. In a bad case, it might be 200 cycles, right? Because if it's not predicted, if it's load or store cannot be predicted well by the hardware, you'll have to essentially pay this price. Okay. So how many registers this Mips instruction set architecture has? It has 32 registers, right? It's a decent number. So it's not large and not small. So typically you don't run out of registers in a typical computation in a function. You might come up with a case where you're computing like long formulas and then you're really like running out of registers. But for most kind of like desktop style workloads like text editors, Apache web server, stuff like that, it's quite rare to run out of registers. x86 has only 8 registers in a 32-bit version, right? And they extended it to 16 registers in a 64-bit version. So x86 again made a wrong design choice. They said, okay, we will be fine with just 8 registers. And the truth is that the couple of those registers are immediately lost for specific purposes taken by the compiler, which is specifically a stack register and something what is called a frame pointer. And then you say, look, I ended up with 6 or 7 if your compiler doesn't compile frames, right? So they made a mistake. So that's why they corrected it, and now they have 64. But it's fine. Like, and again, there are specific practical reasons for why you don't grow this register space. We'll come back to it in a little bit. So one is that if you have a lot of registers, encoding the register number will take space in your instruction, right? Essentially, remember, I kind of hinted on it, but each instruction on this Mips machine is actually 4 bytes. Do we know bytes, by the way? We do or we don't? And 4 bytes is called a word. And I think I have a slide on that, right? So that's a little bit of notation again. So just to make sure we're going slow, right? So remember that data is kept as either a high or low signal in all these circuits, right? So essentially, you can and we will design in this class memory, which can either remember that it's either in a low state or a high, right? So that's why you represent everything as bits, right? And 8 bits form a byte, right? You can sometimes write it as 8B or 1 byte, right? Or 8 bits equals 1 byte. 1 word is 4 bytes, just again, convention, or essentially 32 bits, right? And then just to make sure that we understand that a kilobyte is, it's 124 bytes or 2 to the power 10. 1 megabyte is 1024 multiplied by 1024 bytes, 2 to the power 20 bytes, and so on. 1 gigabyte is, right? Got it? So we understand this, right? So bits are tricky a little bit, right? Because I mean, I don't know how tricky it is to you, because if you understand the binary systems, right, then it's kind of natural. But typically for us, a natural system is decimal. We have 10 fingers. It's easy to count. That's why it's so easy for us to multiply by 10 and stuff like that, right? That's a historical reason. For computers, it's much easier to operate in a binary format, right? Just because you can operate on a bit, each bit individually, right? And then like accumulate or carry and stuff like that, right? We'll take a look at it. Okay, we got this, right? So as I was saying, each instruction is 4 bytes. It's again, this design principle that we will keep everything regular in this machine. Each register is also 4 bytes long, so 32 bits, right? So which means that typically you operate on numbers which are from 0 to 2 to the power 32 minus 1, right? Because that's what you can represent. And I'll come back to this in a second, right? So in practice, if you want to like, sometimes if you say, I have 2 values, B and C in 2 registers, and maybe they're coming close to the max, you know, to this 2 to the power 32. So what happens if you add them together? Because the destination register is also only 32 bits. So clearly, if you need, like, imagine you had 2 numbers, they like start with 1 here and lots of other ones and zeros. When you add them together, if you remember the rules of additions, so there will be a carry here, right? So you need one extra bit here, right? And it's called an overflow. So at this point, you're kind of running in a corner. And if your computation kind of hits the overflow, it's up to you. It's up to the layer of the software stack. So the machine itself, this machine which we're talking about, this Mips machine, will just signal an overflow. It might raise an exception, or it might, you can silently suppress it. And then, you know, like in C, for example, that's a common problem. Like C just tells overflow, all good, keep rolling. And then you start accessing, you know, some random memory just out of, just randomly. But essentially, you got my point. So it's up to the compiler, language compiler, and the operating system to tell you to somehow handle the overflow. The hardware will simply signal. So what will be the solution at the level of the compiler or language, for example? How would you deal with this? If you really want to keep this number around.
You'd have to like look for that overflow exception.
Yeah.
And then make like another space in memory to hold the overflow.
Right. So what your classmate is suggesting is that you, for example, come up with a software library which handles the overflow and emulates infinite numbers. And that's okay. And I did it like once when I needed it really. But what's the disadvantage? It becomes slower. Emulating anything in software becomes slower. So if you can fit in those 32-bit registers, you're golden. You're going fast. If you have to compute something with greater precision, you go into software emulation. But you have to do that if you want to get precise answers, right? And so C is definitely underdefined. Newer languages like Rust, they will be more careful. They will not allow an overflow without an exception, right? So, but C is notorious for them. Okay, so we get it. And also we get, remember I was coming up with those names of registers. I was using T0, T1. So in this MIPS architecture, so registers are not named simply register 0 through register 31. They are given some semantic names. Semantic means that there is some meaning behind the name. And so T stands for temporary. So you have 10 temporary registers, and S0, S7 are like kind of registers in which you put the variables. So typically an idiomatic assembly code would load something from memory from an address where this, remember, let me go back to this picture just for a second. So when you, for example, load B in memory, instead of R1, you would put something like S0. Oh, sorry. We'll put something like $S0, right? That's your idiomatic style. And if you're running out of space here, so instead of like, imagine like you using S0 and let me just move this one, S1, your idiomatic style will be put it in a temporary register 0, right? Although like you're free to like abuse this convention, but it's probably will simplify readability of your code, right? Good. And so now we kind of moved a little bit closer to the real machine instructions, right? So as I was saying, so in order, all these additions and subtractions, they operate on registers, right? So you will have two instructions, so load a word and store a word. So they have a slightly different form. Remember that all my previous instructions had some name of operation here, and then 3 arguments, right? Operand 0, operand 1, and operand 2, right? But this one has only 2 arguments. And that's kind of logical, right? Because you say, look, these ones are simply take an address and bring it to a register. You don't have another operand, right? So there is only simply 2 arguments. So this is an address where the compiler put this variable and you load it into a temporary register. I would write S here, to be honest. And similar, if you store something, you say it's currently in register T0, you will store it in memory in the location pointed by the register T0, right? So is that clear? Okay, question.
Is word always 32 bits or on 64 memories?
Like the question, if I understand it correctly, what you're saying is what you're saying is that what is the word on a 64-bit machine? Yeah. Good question. I think it would be normal to say that the word is 64-bit, but I'm not sure. Like, and maybe there are some disagreements on how it should be called. I remember those discussions about the C compiler and stuff. I don't remember anymore. But imagine we're right here. We're only in a space of 32-bit programs. So everything is 32-bit. Registers are 32 bits. All instructions are 32 bits and stuff like that, right? And essentially, back to my figure, which I was drawing before. So essentially, the compiler. And its compilers are actually a very fun topic. So like I suggest to take a compiler class and at least build one compiler in your life. My funny anecdote. So I built a couple of compilers, but at some point I wanted to build a compiler so badly. So I came up with a language and I actually built a compiler for this language. And 2 years later, I wasn't able to read this language. Can you believe it? So I came up with the language that I was the only creator and user of that language, and I wasn't able to read it. And I should post this. I should post the article. Like I published it as a paper while being a student. You will be surprised. I looked at it. I said, "Wow, man, achievement of science, right?" Was accepted, peer reviewed, good reviews. Anyway, but people come up with good languages, right? And so. Sometimes compiler essentially keeps track of how many variables you have, right? And allocates space in this essentially in this region, which I was calling a data region of a program, right? And just to make sure that we understand the whole life cycle of the program, right? So let me go back here, and I was trying to hint on how it works when in my introduction. So essentially, when you power down your machine, right? So everything is on disk. You don't really have the memory is dormant. So because it's not, it's a volatile memory. It's in some undefined state, right? So essentially, when you boot the machine early on, there is a region of memory which is actually non-volatile, and this is where the CPU gets the very first programs, right? From this region is called BIOS. So essentially, basic input-output system stands for BIOS, right? So this sits in a special region of memory, which can survive reboots, right? So, but then essentially, like operating system kicks in, and your programs, this representation, to a degree almost unchanged, modular linking and loading, which we'll cover a little bit later in this class, sits on disk, right? So essentially, it will be sitting on disk, right? And at some point, some part of the operating system will load it in memory. If this is your memory, right? Your DRAM, it will be loaded from disk into memory, right? And then you will start operating, right? I just wanted to make sure that everything is sitting on disk. There is a step of loading. Sometimes it's a very primitive step, and sometimes it's more involved with you using dynamic libraries and stuff like that, right? But this is how it works, right? So, okay, we clear on that? Like just lifetime of a program slightly. And of course, like if this program which you loaded is a C compiler, right? Maybe this thing itself is a C compiler, then you can pass another program as an input to this compiler, and this compiler will generate output, and it will also be saved on disk as a new program, right? Which you can execute like in the next second, right? Okay, let's go back here. Okay, so, and I kind of drew this picture about like before, like there is a stack, there's a heap. Heap is, again, so I have to jump a little bit forward because I cannot explain stack and heap. To explain why we need stack, I need to explain procedure calls, kind of like function invocations, right? I don't want to do it today, so I will do it next time. And to understand heap, you kind of have to take an operating system class, but I still just want to bring these two together here. So right now we talked about the static data, those int A and B, which are declared in a global scope of a program or declared with a static keyword, right? But who can tell me what are those dynamic variables or dynamic data which is on a heap? So what kind of variables are placed on a heap? Who can tell me? Anyone else besides this gentleman? Okay.
Linked lists and trees.
Anything. So it's not about the data structure, but how you usually allocate memory. You had it.
Is it stuff that's like scopes, things like class?
No, not quite. With the new keyword, right? Exactly. So allocation on a heap is in a high level language like C++, you will use the new operator where you say, for example, A, and that will allocate an instance of a class on a heap, right? And in a lower language like C, for example, instead of this new, you will be using something like alloc and free, right? Right. So those are, you're right when you said that it can be linked list, because it's pretty typical, because you say, why is that typical? Because you don't really know the length of the linked list in advance upfront, right? Because it depends on the input. Maybe it will be 10, maybe it will be a solvent, right? And so you will be running in a loop, allocating more and more variables on a heap, right? So we got the point about the heap, right? Agreed? Who can tell me which variables are sitting here on a stack?
Primitives.
What?
Primitives.
Primitives. What are those primitives? Okay,
Well, it depends.
that's one
Because
version.
If you're in C++, all the variables automatically go to stack. Okay? Unless you use a keyword, and then they go to the
That the second answer was a little bit closer, so I wanted to hear a version. Actually, okay, hold on. There is some kind of a confusion here. So people are confused about the types and the allocation space, right? they are orthogonal. Any type can be allocated anywhere. It just probably you're following the common case and you're trying to kind of reverse engineer and tell me, okay, small variables are typically allocated on the stack, right? And larger variables are allocated on a heap. Although it's not always the case, and you can write programs which allocate bigger objects on a stack, and there are some like pros and cons about it for each version. So you had a, yeah, you can.
Memory, like, or I mean, like addresses, like one stack.
Okay, let me just quickly, maybe I have to come up back to this again. Despite the fact that it looks that it's kind of off topic, it's kind of critical. So let me write you a program. Imagine it starts with something, I don't know how you start a C, is include something, right? Imagine I write int A and B. Those are global variables. And they will be allocated in the data section. Imagine I write something like foo, which takes an integer as an argument, and maybe even returns an integer, right? Let me just move it slightly. It kind of has a variable here, C, which maybe takes A plus 5 and recursively invokes foo with this C argument, right? Right? And so do you understand that each time you invoke foo recursively, right? There might be like some infinite number. Let's make it a little bit more concrete so it doesn't like, because this is definitely an infinite recursion in my code here, right? But we'll do something like something like this. We'll do something if C is greater than let's say 1,000, then we'll just return, and for whatever reason return C, otherwise invoke foo of C recursively, right? So C is kind of growing in this invocation because we keep adding 5, right? Do you understand that there will be like instances of this foo which maybe we invoked with 0, and then the next foo will be invoked with 5, right? Because we did 0 plus 5 here, right? And then we will invoke foo with 10 and so on, right? So each instance of this foo needs an instance of this variable C, right? And this is what I've heard in this class. So you said something scoped, right? So this variable C is actually scoped within a function, right? So this is a function scope. And so, but like you can't really say, okay, this will be a single location in memory, because each invocation will needs a new region of memory, right? And so that's why you have to allocate them every time you do an invocation. You have to allocate additional space for this variable, right? And this variable is allocated, C is allocated on a stack. This is why we have a notion of a stack. So essentially, every time you invoke a function, you might need a little bit more space dynamically, right? Agree with me? Okay.
Do arguments go on stack?
Do arguments go on a stack? That's a very good question, and it depends. So typically, there's thing which is called a calling convention. It's agreement on how you pass arguments. And typically, in order to make it fast, you say, if you have a function bar and it has some number of arguments like A, then int B, int C, and so on, the convention typically tries to place those first arguments in registers. Let's say, I think, I forget what A0 it's called on Mips, right? And then A2 or A1, and then maybe A3, right? But then at some point, if you created a function with a ton of arguments, you keep running, you will run out of space. And then you start passing those arguments on the stack. So for simple functions which don't take a lot of arguments, an efficient calling convention will try to avoid touching the stack, just to optimize the invocation, and will pass everything in registers. Right, in a common set case. However, x86 32-bit version is notorious for that, and they were actually passing arguments on a stack. Again, wrong decision on, but they fixed it in the 64-bit version. Right, that's a good question. Okay, we got the point. So we know now, we kind of have an understanding for what stack is. And if I squeeze like a new operator here or a malloc of size 64, for example, which will be, I don't know, allocating memory for some pointer P, that will go on a heap, right? Did we get this? And again, we'll come back to it. So don't get worried too much that if you didn't understand it fully, but I wanted to make sure that we have an idea for why we need stack. So who can summarize me, why do we need stack? In one sentence.
Because we don't have enough registers to do all the operations, especially when they're next to.
That's one reason. So sometimes you can run out of register space and you want to save them maybe on a stack as well. But I would say that's not the most. I agree. Maybe it's equally correct answer, but maybe let's hear the second one. Yeah. That's a great answer, although I didn't actually mention it myself. So what your classmate is saying, that you have to keep track of where to return, because when you do this operation, which is return C here, you actually you need to know where to go. But my answer, which I wanted to hear, is that you will be allocating local variables in the stack, just because you say each invocation will need its private instance of those local variables. The global variables are shared across all invocations, right? So if you write into this A here, which is funny because that's a bad kind of example, because this A will refer to this local scoped A. But let's assume this is not A, but something like D, right? If you write to this D, it will be changed for all the subsequent invocations as well. But if you're invoking this function for recursively, this C will have a private instance for each invocation of a function. Okay, we'll come back to it, but at least we're almost there. Okay, so back to this, right? So this. Okay, any questions about this drawing for now? And I promise that in the next, maybe when is that, on Monday, we'll come back and I will explain function invocations. It's kind of a tricky topic, so we will come back to make sure that we hear about it at least twice. Question.
I just want to double check. So the F, D, that's global variables, are they on the stack or the D?
Which ones?
The global variables?
D and B. D and B are global, right?
So are those on the stack or the D?
Okay, who knows where those are? In a data section. So there is a special data section which keeps all the global variables, which a kind of compiler was able to track them and say, okay, they will exist for the entire duration of the program, right? Those variables which are here, the ones which are allocated on a heap, they might live for a short amount of time, right? So you might allocate a linked list, pass it around between invocations, and then deallocate it, right? So they will be allocated on a heap, and maybe the same heap memory will be reused for something else, right? You did it multiple times in C++ class, I'm pretty sure. And finally, the variables which are scoped within the function, which are called local, they are allocated on the stack, because you know that you need them only for the duration of the function. When the function returns, you just deallocate the space on the stack.
So is this memory organization just for one program, or is this for the whole computer? Like, is there one stack on the whole computer, or is it each program have their own like mini stack?
Yeah, not typically. Each program will have its own mini stack and mini heap and mini data section. Just because logically you think, even if your machine runs multiple programs like we do today, they're kind of logically independent. And sometimes you only establish a region of memory which is shared between the two programs so they can communicate by writing into this region and reading from that region. So essentially, every time you start a program, roughly speaking, the operating system which you're running will create this organization for program 1. If you start a program 2, operating system will keep track of available memory and will essentially do the same trick for the second program. Again, allocating the text section, allocating the data section, and managing the heap and the stack in some other region. I will ask you another tricky question. What if you're running multiple threads of execution in a single program? How many stacks you will have?
Would it still be fun, but they have
No, each thread will have its own private stack. Because when you will be switching between them, you'll kind of save the, it's kind of, think of it as a private scratch pad. You imagine you're writing a book and you wrote some ideas about it, and suddenly you have to do a homework and you switch, you save this thing, you're the CPU, but executing a different thread of execution, which is now a homework, and you're using a different scratch pad. And then you come back to that first scratch pad saying, okay, I remember where I left, and then you continue. So this is how threading works. We'll come back to it as well, I hope. Question?
one thing that happens, like you said, when there's threads, essentially, have their own separate stacks, but is it possible for some threads or some various threads to like be
What you're really saying is that can one thread of execution access the stack of another thread, for example, right? It's possible, but it's typically called an unsafe operation, because in many languages, it's even undefined what can happen at this point. It's roughly kind of like data comes out of nowhere, you know, maybe you hit by lightning and 0 flipped to 1, but maybe it's a write from another thread. So unless you synchronize carefully, it's unsafe. So I would avoid doing that, but people do still.
So when you're sharing data between threads, is that directly done in the data section or on the heap? Or
Both, can be both. Stack would be very unsafe to share, but typically heap and globals are shareable. We'll come back to that as well. So to multi-threading. Okay, so we got this point. So the high level, like the highlight of this slide, despite the fact, or like not despite. So this is important. So I really ask you to remember at least some version of this picture. However, additional bit of information here is that this Mips architecture has a special register. I mean, you feel free to abuse it in any way you want. You can put it in a in a addition, subtraction, any register can participate in those operations. But typically this global pointer in canonical Mips is reserved, and it points to the beginning of the data section where the global variables are. Why is that? Because it's typically used frequently, and they decided, okay, let's use this register like that. So for example, I'll get to this example in a second. So what I wanted to highlight here is that this load instruction can have an offset as well, right? So both operands can be any registers. Right now I use T0, which is in canonical Mips is temporary registers, right? Used for temporary values. What's important here is this constant 8. So really the address of this instruction, of this load, is not T0, but not T3, sorry, but instead T3 plus 8, right? Why is that? Why is it convenient to have this instruction, which uses, this one is called an immediate offset, I think. So what do you think?
Well, at least like you can see if you have like I can't remember if it's a list or array, but like stored in memory, it's just
Right.
one variable after another. So don't access the next one, you just add one to the address.
Exactly. So for example, this T3 can be pointing to the beginning of the array. And then you, for example, can say, you know, element, like if each element of the array is 4 bytes, so maybe element number, if this one is 0, this one is 1, and this one is 2, which is at offset 8, right? You are accessing element number 2. Agree? And it's the same with this store instruction as well. So you can put a constant here. It can be actually a negative constant, right, as well. So, but the same thing, right? And it's convenient because let's take a look at this example in which we say we have 4 global variables. A, B, and C are integers. Each integer, by the way, is 4 bytes, right? 32 bits. And we have an array of integers, so array of size 10. So the program which compiler will generate and assume here that the data section is stored at the base address 1000, right? So here we say another magical register on MIPS 0 is always just wired to produce 0. You cannot write into that register. So it's always 0, whatever, no matter what it takes. So it takes what it says, okay, 0 plus 1000, put it in this global pointer register, right? So kind of initializing if this is your memory, and you say that your data section starts somewhere here at address 1000, right? So essentially initialize GP to point right here, right, to 1000, right? And then you say, okay, if you want to access A, you say GP plus offset 0, bring it into S1. If you want to access B, and it is, imagine again, just it can be different. So the compiler actually, it does not guarantee that those variables will be allocated in this specific order in the data section, but just for the sake of example, imagine that it happened this way. So essentially, since each of those is 4 bytes, right? So then B will be sitting at the offset 4. So we're using this GP as an offset, loading it, GP as a base and 4 as an offset, loading it into S2. C is at the offset 8, loaded into S3. The value D0, which immediately follows those A, B, and C, is at the offset 12, loaded into S4, and this is D1 loaded into S5, right? So this is how imagine this is the very beginning of your program, and for whatever reason, that's your, I can say main function. In practice, there is a ton of things in most cases which execute before main. Like for example, your constructors of your static classes, right? They have to run before main because maybe they have to open a file or something like that, right? But imagine we have a simple language like C, and C also allows this behavior. But let's imagine that main, we disable this and we just run main, and this is like the beginning of main can be very well similar to this one. Initialize the global section and then keep running, right? Agree with this example? Any questions about it? All good? Simple. We'll take it easy. So what do we need to do this? So essentially take D2, add A to it, and write into D3. How does the code will look like? It's, again, I believe that almost everyone now thinks, okay, I can do that because it's not that hard, right? So, and we literally have what is it, 4 instructions: load, store, addition, and subtraction, right? And it's easy to keep in your head, right? So the assembly language can look something like, again, offset 0 from GP, load into S0. D2 is sitting at the offset 20. Remember, because D0 was sitting at the offset. This was 0, this was 4, this was 8, so this one was 12, right? So this one 12. D1 is, what is it, 12, 16. D2 is offset 20, agree? Right? So offset 20 into S1, the sum of these two is S0 plus S1, put it back into S2, right? And then store S2 into D3, which is at the offset 24, right? By the way, I will ask you to write those programs, right? That's why I spend so much time, but I also want you to understand how they work internally. Okay, cool. So we know everything about this. So let's spend a little bit of time. Okay, so today I will only cover these 4 instructions and a little bit of a binary encoding, right? And then next time we will talk about control flow instructions like jumps, comparisons, conditional jumps, and hopefully we'll get to functions, right? But so far, so good. It's all linear. So it's kind of like you execute instruction by instruction and there is no way out, right? There are no jumps, nothing. But we understood the memory. Hopefully we have some idea about the stack. It will become reiterated when we start invoking functions. We kind of have ideas about heap, dynamic variables with new or malloc, and we understand where the static variables are, right? So now let's talk a little bit about how we represent numbers, right? So did you guys take classes on binary systems? So you know this already, or it's still new? Yes, new? Okay, so computers operate on binary numbers. So what is a binary system, right? So ours is our natural system is a decimal, right? So binary works like that. So if you take the least significant bit, or bit number 0, right? You multiply it by 2 power 0, which is always equals to 1, right? And this is the encoding. If it's a 0 here, then it's 0 by 1. It's results in 0. In this example, it's 1, right? And then you go in those powers. So the next here will be 1 multiplied by 2 power 1. And plus 1 multiplied by 2 power 2, and so on, right? So it's a decimal system works exactly like that. So instead of 2 here, you will have 10 to the power 0, which is always 1, multiplied by whatever position of, like, imagine you have 125, right? So that will be your 5 will be here, plus 2 multiplied by 10 power 1, plus 1 multiplied by 2 to the power, oh, not 2, come on, 10 to the power 2, right? So essentially what it means is that you say 100 plus 20 plus 5, right? Right? That's your number. That's how you represent in a decimal system. So in a binary system, the logic is the same. You just, instead of powers of 10, you use powers of 2, right? So, and which means that, you have 32 bits from bit 0 to bit number 31, right? And you can encode any range of numbers, right? But typically you want to encode the numbers which are most frequently used. So you encode something in the radius of 0. So for example, if this is 0, you say, I might encode a little bit of negative numbers and a little bit of positive numbers. Or if you don't care about the negative numbers, you just go forward from 0 to 2 to the power 32. That's the max. The max number which we can represent is all ones here, right? And that will be like 1 to the power of 231, and so on, right? So it's roughly 4 billion if you care, right? So you got the point about the systems, right? So you understand how to convert between decimal and actually I never explained how to convert. Skip it. Use the calculator how to convert. I mean, really, this is important to understand. So how you convert from binary to decimal, right? So just to understand that it's the same number, right? And so you can choose which numbers to represent, as I said, but you typically want to represent something, what means to you, what you use most frequently. So 0 is logically, let's represent 0 as all binary zeros, right? So that's kind of human friendly. 1 in decimal is just 1 bit, right? Because it's exactly 2 to the power 0 multiplied by 1. So which means that it's 1 multiplied by 1 equals 1, right? And all the other powers are zeros, right? So everything else will be zeros. So the max number will be, the max possible number will be, for example, all ones here, right? If you decide to represent negative and possible numbers. There is a little bit of a trickery here. The trickery is the following. So how would you represent negative numbers if you care about them?
If you want negative numbers, you need to get the last state available and have it.
Right. So what you're suggesting is, let's say one bit, let's assume the most significant bit. And if it's 0, maybe the number is positive. If it's 1, the number is negative, right? Agree? What's the problem with this representation?
If you're adding numbers, it makes it a lot harder, because if you want to add like a positive number and a negative number, with that representation, you have to do a subtraction actually. But if you look at like the way it's showing on screen, you can actually add a negative number to a positive number and it will work.
Right. So, okay. First of all, if you say that this bit controls the sign, you first of all running into a problem that additions have to be handled specially, because you need to have some additional logic on your CPU to decide, are you adding positive to positive or negative to negative or negative to positive, right? That's kind of ugly. But another ugly property of this representation is that you will have 2 zeros, one negative 0 and one positive 0, because supposedly no matter what you put here, if all of those bits are zeros, right? But whether you put 1 or 0 here, it's still 0, right? According to your representation. That's also kind of ugly because even comparison with 0, you have to additional circuitry to make sure that you like disregard the bit. And so they came up, they first tried those. So it's not like everyone was thinking similar to how you guys are thinking. And architects tried these representations, but came up with a better idea. This idea is called a two's complement, in which they say, look, the -1 will be represented as all ones here. The beauty of this representation, if you add 1 to this line, so if you do something like -1 plus 1, and your 1 is really, okay, let me just go back. I don't know why I decided to walk back and forth. So this is your 1, this is your -1. And if you're adding this 1 to this one, you naturally arrive to 0, just because it will carry over to the overflow bit, and then you get to 0, right? So your addition in this representation can like actually handle, like, it doesn't care about whether it's adding like negative to negative or negative to positive or positive to positive. It just works, right? Because this is how the rules of like bit addition work here. So -2 will be represented like this and so on. So minus the largest negative number, it's kind of like, again, you still have this control that if this bit is 1, then the number is negative. But the representation is specific in such a way that -1 plus 1 gives you 0, right? So how do we convert now from positive to negative numbers, right? So if I say that so the conversion, this representation is called two's complement. So essentially what you have to do to convert a number is to take a complement of a number and add 1. Meaning, for example, if you say I need to do, imagine there is like a ton of zeros and this is 1. Imagine you want to represent -1, right? So you say do a complement, so each 0 switches to 1, right? This one switches to 0, and you plus 1, you arrive to the number which we want. It's all ones, right? If you want to do something like some other number, let's imagine negative, this is 7, right? So if you do a -7, you take a complement, so switch all the 0s to 1s, all the 1s to 0s, and add 1, so you will get 1, 1, 1, 0, 0, 1, right? That will be a -7. Why does it work this way? Who can tell me? There is a cute observation about it. Can someone tell me? The observation, if this symbol is it represents complement, do you believe that number plus its complement is always -1 in this system? Do you know why? Why? Yeah.
You'll end up with all ones.
Yeah, it's -1 is all ones. So why do you always end up with all ones?
Because when you add the complement, you have 1 plus 0.
Exactly. So do you see this observation? Let me go to this whiteboard here. So imagine you have a number, no matter what the number is. Like, let's imagine it starts with 1, goes 0, 0, 1, 1, 0, 1, right? If you take its complement, this 1 turns into 0, this 0 turns into 1, this 0 turns into 1. We don't care about this. This 1 turns into 0, this 1 turns into 0, this 0 turns into 1, this 1 turns into 0, right? If you're adding them, you're always adding 1 plus 0. It just in one, it can be either on top or at the bottom, right? So you will end up with a number which has all ones, right? So if this is x and this is x complement, right? So this one is 1. So you have this logical formula that x plus x complement equals 1, right? Oh, sorry, -1, sorry. Okay, -1, right? And now you can work your way from here. You say, look, I will move this x here. You will end up with x prime equals -1 plus, oh, sorry, -1 minus x. Then you move 1 here. So you get x plus 1 equals minus x. So essentially, that's your formula. If you want to compute minus x, you take a complement and add 1. That's the shortcut for how to compute it, right? Okay, good. So this is clear. A little bit convoluted, I agree, but kind of cute that it works this way. You can very efficiently compute those numbers. Hold on, just a couple of examples before we go. So we'll probably have like 1 minute. Yeah, 3 minutes actually. So again, 5. So remember our basis. So this is 1 multiplied by 1 plus 2 multiplied by 0, because this is 0, this is plus 4 multiplied by 1, right? This one. So you get 5 because it's 4 plus 1 equals 5, right? What you do for minus 5, so essentially again, you're flipping all zeros into ones, flipping and adding 1. And when you add 1, you will have a carry. So that's why you will get, no, you don't have a carry here. So it will be 0, 1, 1, right? Because you added 1. So similar to 6, it's the same, but you will have to add yet another number here. Okay, so I will be asking this. Okay, let's probably get to this next time because otherwise we will forget about it. Okay, hold on for a sec. So are there any questions? A couple of good things happened. So first of all, TAs and I myself figured out our office hours. So mine are right here, starting at 1:30 in my office. It's in the Merrill Engineering Building on the 3rd floor. I think it's 3220. I actually don't remember the number, but look, hold on, like on Canvas, don't go away. TAs are useful. We should use them. On Canvas, there is a schedule. And the other thing, again, UCI. The other thing is that I promised that I will be putting the PDFs before I can come to the lecture. So I actually did today. So if downloading just works for you, that's it. Okay, thank you. See you Monday. Oh, not Monday, Wednesday.